Boolean logic, try to simplify them, and also implement them in the form of circuit diagrams. So it's possible for us now to understand Boolean logic and to devise simple devices so that we can carry out small automation related tasks, maybe even bigger ones. You go to industry with what you have already got now, you will be in a position to at least understand how many of the devices are configured and what is the logic. Now the next point, see, we were here in the digital computer and we were trying to understand the digital world. We assumed that signals were available as ones or zeros. So essentially, we had digital inputs and we could produce digital outputs. Now, we need to connect to the analog domain, to the analog world. We need to connect our digital world. One of the most important devices in this connection is the operational amplifier. And that will help us to connect from the analog world to the digital world. Now, we can use it in two ways. We can base our analog to digital converters on the operational amplifier, and we can also do our digital to analog converters based on the operational amplifier. So the operational amplifier is very fundamental, not only for this conversion, but it's also useful for signal conditioning, filtering, amplification, offsetting, etc. So the operational amplifier is an extremely important device in the framework of mechatronic devices. So let us try to review the operational amplifier that we have already studied, possibly in the first year. You must have done it in your basic electronics course, I suppose. Now, suppose let us consider a symbol. Usually we have the operational amplifier is actually represented using a triangular symbol, and I'm going to just prepare one triangular symbol like this. Just keep it handy. Okay. Yeah. So you are already familiar with the symbol of the operational amplifier. Now, in this device, we have two inputs and one output. So we can show these two inputs. We have input here, another here, and one output. Now, these inputs, so usually we say that this is the non-inverting input and this is the inverting input and this is the output. Okay, so this is the output. So this is the inverting input. And this is the non-inverting input. Okay. So there are these two inputs. Now the operational amplifier is actually a very simple device. What we have just shown here is the symbol of an ideal operational amplifier. So this is actually an ideal operational amplifier. It's also written as op amp in short. Okay. Of course, certain other connections are not shown. The supply connections are not shown. Now, suppose you have, let us designate this input as, let us say the potential applied here is Vp, and the potential here is Vn, and the potential here is, let's say, Vo, V0 or Vo. So we will have a relationship between these potentials when we use this operational amplifier. Now, there are only two significant principles of the operational amplifier, and that's what makes it a very useful, a very versatile device. And we will see that in this lecture. What are those principles of the operational amplifier? Now, there are two principles. First is that it's a very high gain device. So, first principle is that it is a very high gain device. What do we mean by a high gain device? That's how the output is related to the input. So you have a very high gain. Gain is a multiplier. Okay. So let's say the gain is A. Okay. Uh, then we can write this relationship as V out is related to the difference of the inputs. So Vp minus Vn multiplied by this high gain. Now, theoretically, for an ideal operational amplifier, A is very high. It tends to infinity. Okay. But Vp and Vn are finite. So if A is tending to infinity, one would expect that V output would also tend to infinity. But we know that we don't apply infinite potentials We don't get output of infinite potentials. In fact, we are bound by the limitations of the power supply to this device. So we don't look at this relationship in this manner. We look at it more like this. That means we look at it in this manner. Vp minus Vn equals to 1 upon A V naught. Okay. So now V naught is going to be bounded by the limitations of your circuit, the inputs. You can't have larger value of potential than what you are applying. Okay. You may apply plus minus 5 volts, plus minus 10 volts, plus minus 12 volts. But you can't get an output more than that. So this V naught is actually finite, but A is infinite. A tends to infinity. That means that by the first principle of the operational amplifier, Vp minus Vn will tend to 0 because A is tending to infinity and V naught is finite. So this tends to 0, and that means that Vp or Vn will try to track each other depending upon which is made, which is forced. Okay. So you may either write it like this, or you could also write it like this. Okay. So this is the first principle of the operational amplifier. So it's a very high gain device, and the consequence of that high gain device is that Vp or Vn will try to be equal to each other. Now the second principle is that it is a very high input. It has a very high input impedance. So this is the second principle. It is very high input impedance. And very low output impedance. What does this mean? Ideally, what do you understand by high input impedance? Can anyone tell me what do you understand by high input impedance? Anybody in the class? Yes? Is there nobody who can tell me what is the meaning of high input impedance? Are you able to hear me? Hello?
So that means there is a very small amount of current that will flow depending upon a resistance.
Right, you're right. So impedance is actually an obstacle. So it's when you say high impedance in our context, it is an obstacle to the flow of current. So when you impede current, you say it is high. When you impede it to a very high extent, that means theoretically you don't allow current to flow through the inputs, but you allow potential. Okay, so it means that your device is just going to accept signals, no power. So it's a very high input impedance device and very low output impedance device. So in this device, if we designate, say, this current as IP, and if we write this current as IN, then we can say that IN and IP both are almost zero. Okay, so they are almost zero. So this is what we mean by high input impedance. And what do we mean by low output impedance? Yes, can anybody tell me what do you mean by low output impedance?
Sir, IO tends to sir infinity.
IO tends to
Infinity, sir.
infinity. No,
It's a very low output impedance, sir.
very low output impedance doesn't
Sir,
mean that.
out
Yes, it means that I output, if we write this current here as output current IO, it means that IO is uh, it's not restricted. So depending upon whatever is the current that is needed to maintain V output, this device can supply that current. It means that this operational amplifier acts like a voltage source. So it can provide any current that is needed to provide this voltage. That is what it means theoretically. So I naught is not restricted, but it depends on what? It means that the op amp functions like uh, is like a source of potential, potential or voltage. So what is the characteristic of a source? Characteristic of a source is that it can provide the necessary, a source of potential would be, it can provide the necessary potential irrespective of whatever is the current that is required to be drawn from it. Okay, so the op amp is like a source of potential. That means it can provide, it can ideally provide I'm not sure whether the spelling is right. Please check it. It can provide, it can ideally provide any amount of current I naught to maintain or to obtain V naught. Okay, to maintain the output potential as V naught, so it can provide any amount of current. Now, these are the only two major principles of the operational amplifier, and they are absolutely they are very important. Okay, so we have the first principle here. Okay. And the consequence of this principle is that we have Vp tracking Vn, and the consequence of the second principle is that it is okay, and means that this is the consequence. Okay, so these are the two major principles of the operational amplifier. Okay, now we will see how to apply these principles when we draw circuits, when we construct circuits using operational amplifier. So let us move to the next. Let us go to the next slide, and we'll copy this figure. We'll paste this figure here because we'll need it now. Let's construct a circuit like this. Um, let's take let's take a very simple operational amplifier. Say we'll take let's say we connect one end. So let's make this as the non-inverting end and this as the inverting. This just, and then let us uh, also let us say that this is V output. We have Vn here. This is Vp. And let us consider it in a configuration like this. Say we have, we connect this to the ground. And here we will connect it through a resistance. Okay, need not copy it. We'll also connect from here. Yeah. So we were here. So let's consider a very simple configuration like this. You have already seen this simple configuration in your electronics course, basic electronics course. Okay, so this is our circuit, let us say, and we have let us say this terminal here, we will say is VI, okay, where we are providing the input. This is the output. And let us also designate these resistances. Let us say that this resistance is RF. It's very standard terminology. It's the feedback resistance from the output to the input again. So it's called feedback RF. And this is the forward one. So usually it is designated as RS. Okay. So we have got these two resistances. Now, in this op-amp circuit, we have not shown the power supplies. Of course, you can connect positive and a negative uh, terminal to it, but I'm skipping those preliminaries and we come straight to this circuit. Now, what is this circuit going to do? If we apply the principles of the operational amplifier to this circuit, what is going to be the output of this circuit? How is the output going to be related to the inputs? Okay, that is the question. So first, let's apply the principles. We'll proceed from first principles. So applying the principles of the operational amplifier, let's apply the first principle of the operational amplifier. The first principle, what is it? It is a high input impedance device, very high gain device. And what was the consequence of that high input impedance? We said that Vp and Vn will almost be the same. Got it? But what have we done to Vp? We have grounded Vp. So the potential available at Vp is what? It is zero. Excuse me. So the potential at Vp is zero because it has been grounded. Now, because of this grounding and because of the imposition of a 0 volt, a zero potential here at Vp, Vn is bound to follow this Vp. Okay. So the first principle says that Vp minus Vn is equal to, or is, yeah, is equal to V naught divided by A, which is the gain of the operational amplifier. And because this tends to infinity ideally, and this is actually limited, it is bounded. And so what happens? That this becomes almost equal to zero, implying that VE, in our case, VP equal to zero. And so this is also, it should also be equal to Vn. This makes Vn not a potential which is grounded directly. Its potential is zero, but it is indirectly, it's called as a virtual ground. Okay. So Vn becomes a virtual ground. Vp is a real ground, but Vn becomes a virtual ground. So this is what we call as a virtual ground. So it has got virtually grounded. So Vn also is going to be equal to 0. And next is we apply the principle, the second principle of the operational amplifier, and that is that it is a very high input impedance device and a very low output impedance device. And to apply this, we restrict the current. So this IN, let us say this is IN, and this IN is theoretically equal to 0. IP is theoretically equal to 0. Okay. So these currents, input currents are zeros. Let us also designate the other currents. Let us say that this current here is IS and this current here, let's say, is IF. Okay. Now, if you apply Kirchhoff's current rule, you will see that IN, which is 0. So here we have IN and IP. Okay. They are, IP is actually equal to 0. So you can IN tracks, or I would rather write it as almost equal to IP, and IP is actually equal to 0. Okay. But we also know that when you apply Kirchhoff's rule, current rule, you get IN, this current should be equal to IS plus IF. Agreed? So IN is equal to IF plus IS. Okay. And we say that this should be equal to 0 or almost equal to 0 because IN is almost equal to 0. Now, what is IF? If you apply the potential difference method here, you can see that IF is actually, it can be written as V output minus, so this potential minus this potential, that is Vn, divided by RF. Divided by RF. See, this current here is actually just this term. Okay. And IS, in the same way, it's this potential difference divided by this resistance. So plus Vi minus Vn. Vn here is a potential at the inverting end divided by Rs. Okay. So this term here is actually nice. Okay. So this is equal to 0. Now we know that Dn over here, because you virtually grounded it in the using the first principle. So this is almost equal to 0, and so is this in here. So you can straight away write a relationship. So you can say that V output upon RF will be equal to minus V input upon RS. And this means what? It implies that V output can be written as equal to minus RF by RS times V input. Okay. Now, what have we achieved using this circuit? We have achieved a relationship between the output and the input. And what is that relationship? The input is related to the output. First of all, its polarity is inverted. If it was positive, this would be negative. If this was negative, this would be positive. Okay, so its polarity is inverted by this negative sign. Secondly, so it is inverting the input. And secondly, this ratio RF upon RS, that means you can choose these two resistances RF and RS to obtain a gain. You can, if RF is larger than RS, you are amplifying the input. If RF is smaller than RS, you are attenuating the input. Okay, so this becomes what we call as the gain. So this is actually a configuration, and this is the gain of this of this inverting amplifier configuration. So this is in an uh, inverting configuration. Inverting configuration. Okay. So we have achieved two things. One is that we can change the polarity of the signal. So first is we have achieved using this circuit, we are able to invert the polarity of the input. Okay. And the second is that we are able to attenuate, amplify. We can, let's say we can amplify. So when does amplification take place? When RF is greater than RS. Okay, so amplify or attenuate. So we can either amplify or attenuate the input signal. And what do you mean by attenuation? It can be achieved when RF is less than RS. Okay. So this is the operational amplifier in the inverting configuration. So this is the first configuration. Let us consider another configuration of the operational amplifier. Does anybody have any doubt in what we have done so far? Any queries, any questions? Hello? Hello? Do you have any
No, sir.
questions?
No,
Okay.
sir.
Okay. So I think we have only 3 minutes left. Let us continue with our other configurations in our next class so that we have continuity. And let us pause here for today.